conductance peaks, and it's perhaps worthwhile to spell out slightly more precisely what kind of setup one is looking at in order to distinguish it from setups that we will be looking at later. So let's take a quantum wire, for example, and let's proximity couple it to a superconductor. And let's also ground this superconductor. So the number of Cooper pairs on this superconductor is not fixed. It can vary. What's fixed is the chemical potential. And then let's apply a bias between the superconductor and the quantum wire after putting a tunnel barrier at the beginning of this wire. So this is supposed to be some gate by which I can deplete the electrons in this wire and create a tunnel barrier, and then I apply a voltage and measure the current, of course, between the normal lead of the quantum wire, the normal part of the quantum wire, and the superconductor. And so the question is how the tunnel current looks that is flowing here in this kind of setup. And what we're dealing with is with a problem in which we are having current flow from a normal system into a superconducting and gapped system. And that in particular means, since we look at small bias voltages that are smaller than the gap, single electrons can not enter into the superconducting region, and hence the current has to, only pairs can enter. And one way that, and maybe I'll be a bit more detailed about this later, but if we're thinking of t equals 0, this is certainly the case. And then the process has to flow by Andreev reflection. So let's sort of sketch the situation that we're having. We have this topological superconductor, which has some gap. Let's just call this delta. Right now I'm not distinguishing between the gap of the proximity providing superconductor and the topological superconductor. Then here this topological superconductor ends, so there will be Majorana. Actually it's one, there's another one at the other end. There's a Majorana sitting here, so that means that there's a zero energy state at the in the superconductor, and now we are probing that from the normal side. And on the normal side, just have a normal Fermi C. And then what can happen is that if the voltage allows, which in this case it happens even at zero bias, or at very small bias, you can have an electron tunneling in. This happens with some rate gamma E. And this electron cannot stay there by itself, but what can happen is that you have a whole Andreev reflected, or that this electron gets Andreev reflected as a whole, and as a result you have a Cooper pair transferred into the condensate of the superconductor. And what we see is that since we have this Majorana state, basically this electron can tunnel into the Majorana state, and this is a resonant process even at zero bias. So we expect that there will be some peak, conductance peak at zero bias. And in order to calculate this, one way of thinking about this is of basically having an electron reservoir, then you tunnel into this Majorana state, and then you tunnel back out into a whole reservoir. So this is some sort of a resonant tunneling process by which you're tunneling through a single state. And for a resonant tunneling process, one knows what the conductance is. And it's 2e squared over h. The 2 actually requires some more thinking. And then you have gamma e, gamma h. You have to tunnel in and you have to tunnel out. If they have both processes. You have the bias voltage squared, because this just tells you how far you are away from the resonance. And then this resonance is broadened because it's coupled to the reservoirs by the sum of the two rates, gamma e and gamma h. Okay, that's the sort of expression that you expect. So basically, you have an electron tunneling in to this Majorana state, and then a hole coming back out. Now, there's one more important point about this, and that is that this Majorana state is particle-hole symmetric. It's half electron and half hole. And this means that so we have particle-hole symmetry, and that means that the rate for electrons to tunnel and the rates for holes to tunnel are exactly the same. So this by symmetry. So we have gamma e is equal to gamma h. And if we have that, then this actually simplifies. So let's call this rate simply gamma without any subscript. And then we have the I dv is equal to 2e squared over h. And then we have gamma squared divided by ev squared plus gamma squared.
So is it important that the mono region is microscopically large?
Well, how do you want to make it microscopic? I mean, it's coupled to a norm. I mean, somewhere there's a wire. Yeah? You can make it longer. I mean, it's effectively longer. I mean, there's some wire sticking out here, right? So that's all normal. It doesn't matter. It's just important that there is a tunnel barrier here. Okay, so what you see is because of the symmetry. So generally, the conductance peak due to resonant tunneling doesn't go all the way up to 2e squared over h, but it stays smaller than 2e squared over h if these rates are different. But here, since we're having a symmetric junction, if you go to set v equal to 0, this factor just goes out, and you have exactly 2e squared over h. Okay, that's a generic thing for symmetric resonant tunneling, and here this is imposed by particle-hole symmetry. So what this predicts, if this is the voltage and this is the IDV, is that we get some sort of a conductance peak. The width of this conductance peak is given by this rate gamma, and the height is exactly 2e squared over h. Now, it turns out that that's the prediction, and none of the experiments ever see 2e squared over h. And so now you can get worried. But actually, there's a bunch of things that we should be taking into account that to do away with the worries. Let me mention essentially two of them from one source. There can be more points of this sort. So, and the basic thing is that what this neglects is that these experiments are done at finite temperature, and at finite temperature, actually, so what I dropped here are all the thermal factors. If you put the thermal factors in, then actually the width of this peak is no longer going to be controlled by the strength of the tunneling, but rather by the thermal, by the temperature. So we have a broader peak, and correspondingly the height goes down. So the height is reduced. This is 2e squared over h times gamma over t. Maybe I should have drawn it in this color. And the width is now controlled by temperature and no longer by gamma. So that's the simplest thing that can happen. But actually, there's more things that can happen because of finite temperature, and that is that it's no longer obvious that the process is happening as an Andreev process. So we have this broadening. And the other thing is that we can have additional inelastic processes that we did not take into account previously. And so let me give an example of this. So one thing that can happen is that the electron tunnels in, and then you can have a phonon or something come along and kick this electron out into the continuum, and then you don't no longer come back as a whole, but it's just a single electron that has gone into the superconductor. That's one option. Another option that you can have is, imagine you have another subgap state that is not at zero, but at some finite energy. And let's assume that this subgap state is actually thermally occupied, and now you have one electron tunneling in. Then these two electrons can recombine and form a Cooper pair. They have to get rid of their energy in some way, again, maybe because of a phonon. But you can have these sorts of Cooper pair recombination processes, and again, you don't have a whole process, a whole tunneling back in this case. So this process, this sort of thing, they have two consequences. One is, or let's call it inelastic. They add another contribution to the width of this resonance, and so this actually suppresses this Andreev conductance below 2e squared over h, because now numerator and denominator no longer cancel at zero bias. And the second thing is that this, of course, is an additional single electron tunneling current that you can compute that would add to this Andreev current. And so both of those together just mean that the result in general will no longer be universal, and you get a zero bias conductance peak, but the height is not something that is very well quantized. Now, it depends a little bit on the kind of system that you're looking at. So in SDM experiments in particular, in the initial ones that were done at 1 Kelvin, I'm almost certain that the entire current flows by these single particle processes, and there's almost no Andreev tunneling going on. At least we have had some paper with an experimental group in which this seems to come out very clearly that is so. In the quantum wire experiments where you're not working at 1 Kelvin, but maybe at 50 millikelvin, this is much less obvious. But also in these quantum wire experiments, and especially in the early ones, there were lots of other, the gap was actually very soft, and there are lots of other subgap states. So this recombination process may also be very efficient in that case. So it's not so surprising that these experiments typically don't see 2e squared over h. I think you have to actually work at it. So maybe
What's the width of that peak in the quantum wire experiment?
So it's of the order of the temperature. I think that let me add one more thing for the quantum wire experiment. I don't want to go into the details, but actually it's a multi-channel wire, and I think there are good reasons to believe that in such multi-channel wires, the effective gamma is very, very small for the channel that actually contains the Majorana. And so it's essentially controlled by temperature in that case. And you're very far away from the actual gamma for the Majorana channel. But you have to look at the multi-channel case in more detail, and I don't think I want to get into that. Well, so this is for, of course, when gamma over t is small compared to 1, right? That's what in that limit I can do that. Now, can I ever get it to be larger than? I don't think it gets larger than 2e squared over h. But so the one thing that may make you worried is the fact that we have this additional single particle tunneling. But I think it comes at the expense of some Andreev current. So I think larger than 2e squared over h sounds very unlikely to me. Right. What are the two channels that are interfering?
Because it can go to the continuum, right? From this goes to
well, but I guess Fano I would associate with having two interfering processes, right? Some direct thing and here I think the final states are different, so they don't interfere, they just add. So I don't think there's going to be a Fano shape here.
Is there any reason to expect some feature other than the height of the peak to stay robust if say we neglect inelastic processes like some area under the curve due to some sum rules?
Well, that's why yes, that's a good point. So of course that's exactly what I mean. So the width goes up by t and the height goes down by t, so that the strength of the peak, the integral under the peak, remains fixed. Okay, so you might think that then you can extract gamma from sort of normal state conductance measurements, right? And t you know anyway, you just measure it, or at least you hopefully know it somehow, and then you should be able to figure all of this out. But that's I think where this multi-channel thing comes in again. That I think the actual gamma for the conductance is determined by other channels than the one that actually carries the Majorana. So I think it's very hard for this experiment. I mean, you can weasel your way out very easily, and I think convincingly, that you don't have to take this area seriously. Yeah.
Actually, isn't like the level for the electron split between the two Majoranas at the end? How can you resonant tunnel to a level which is
Good.
localized?
This question always comes. Good. I'm going to run into time trouble, but let me. I think it's a good thing to do. So I think that one way of understanding this, why an electron can sort of go into the Majorana, it's bad language, and you should think about it differently, and then there is no problem like this. And so in order to do this, let's actually do what I think I almost did it. No, well, let me exaggerate it a little bit. So let's leave some finite region here that is just normal and not covered by the superconductor. Okay, and so now let's think about what's actually happening. Let's imagine we come in with an electron here. It has some chance to be reflected. That's not interesting, but it has some chance to be to tunnel into this normal region. Right, then it will travel in the normal region, and then it will hit the superconductor where there's a gap, so it will get Andreev reflected. Right, so let me actually, maybe I draw this differently. So I have more space. So this is the lead. This is the barrier, which actually I should maybe, let's make it a bit narrower. And this is the barrier. It's this normal region actually, just to call it normal. Okay. So we come in as an electron. We tunnel in. Actually, maybe I do want to give it the barriers, because then I can. So it's sort of the normal region, but I want to give the t the amplitude that is associated with this tunneling there. So I come in, and it has some amplitude Te. Then it gets Andreev reflected. So it comes back. So we have some reflection from electron to hole. Then we're propagating as a hole. Now, one possibility is that this hole comes back out, which will be T hole, and this contributes to the amplitude for having Andreev reflection from this entire system, right? But then, of course, more things can happen. We can again reflect from the barrier and come back as a hole and do another Andreev reflection. So this one is R hole, and then we can now either go out as an electron. Then I haven't done anything that's not interesting because there's no charge going anywhere. The charge that went in comes out. So I need to do this again. I need to reflect as an electron and have another Andreev reflection as a hole, and then go out. Okay? And then, of course, I can continue with this. This can go on indefinitely, and I have to sum all of these things up. And if I do this, now let me see, can I do this? So I have T hole, R hole electron, T electron, 1 minus for this entire geometric series. And then now this starts probably with a hole that is reflecting. I have, let me rather look it up. It's Ashwin seems to get all of his things off the top of his head, but I RHE, RE, REH, RH. Okay, so this is the a microscopic way of just deriving this equation, and I don't want to go all the way. But let's now have a situation in which RE and RH actually let's close the barrier or make the RE and RH almost one. So we only keep this this transmission very small, but these things we set equal to 1. Okay, then we have the denominator here is RHE, REH. And now, if you're at E equal to 0, you can show that REE has to be RHH star, and REH is RHE star, if I remember. So this is just big E equal to 0. You have particle hole symmetry, so this is and unitarity, and this is what you get. So what you find is that the determinant of R, which is a unitary matrix because you cannot transmit into the superconductor. Everything has to be, this is the reflection matrix from the superconductor. Okay? Everything has to be reflected. Nothing can go into the superconductor. And so it's a unitary matrix, but the determinant is real because it's REE, RHH, which is REE absolute value squared, minus REH, RHE, which is again absolute value squared. So this is real, and then there are only two possibilities. It's either plus or minus 1. Okay. No, it's not a gauge trace. It's a symmetry. So you know that it's unitarity and the fact that you have particle hole symmetry, and the particle hole symmetry implies symmetry on this reflection matrix, and what it implies is together it implies these relations. Okay, and so this basically tells you that you have only two possibilities to do this, and basically you have REE equal to 1 and REH equal to 0, or you have REE equal to 0 and REH equal to 1, absolute value, everything. Okay, so this is basically pure normal reflection, perfect normal reflection. And this is perfect Andreev reflection. And it turns out that this is what happens in the trivial phase, and this is what's happening in the topological phase of the superconductor. Okay, so this is actually this determinant of R is actually a topological index. It's another way of defining a topological index for such a 1D system by looking at scattering from the outside. So this is trivial, and this is topological. So now let's assume that we're in the topological phase. So REH is equal to 1. That's the only possibility. So we find that this is equal to 1. So we see that the denominator actually blows up. And that's the Majorana resonance. That's exactly the sign that you have a Majorana resonance at that energy. But now in this problem, I never said that an electron is tunneling into a Majorana state. All I did is an electron tunneling into a normal region of a wire, and that's perfectly okay. And then the Majorana forms because you have all this Andreev scattering from electrons into holes, and that's what generates the Majorana in the end. So I think in this picture, you never have to say any of these funny words that you may or may not want to understand. Good, and you can complete this calculation in a few lines and show that it actually reproduces this exactly.
Why do you expect RH equals to 1?
Pardon?
Why do you expect
Well, the RE is and RH is just that if you have a very, very strong tunnel barrier, I mostly reflect. And I only have a very small probability. So the Majorana, of course, is only perfect exactly when you close this off completely. Then you have to have a Majorana at the end, a perfectly well-defined Majorana at the end of this topological superconductor. And then you have an exact divergence, right? But if you keep it a little bit open, then of course this argument was not completely correct. And the amount by which it is open, you go away from this divergence, and that's exactly the transmission through the barrier gives you the width of this resonance. Okay, that's how it works. Okay, good. So now let's change the setup a little bit and do the following. Another thing you may naturally think might be interesting is to have a tunnel barrier here. Proximity couple it to a superconductor. And now, instead of grounding the superconductor, let's leave it floating. Or rather, if you want to have more control, let's put a gate voltage on it that controls the charge on the superconductor. So we have some capacitance, gate capacitance. We apply some gate voltage, and then that goes to ground. Okay, and then now we cannot measure the current between this lead and the superconductor, but rather we have to go between this lead and the other end of this topological superconductor. So now we apply the bias between this end and that end. Okay. So the reason why I want to discuss this is basically because, first of all, there's interesting new physics associated with it. Something that Liang Fu called electron teleportation. It's a nice name. And it also, this charging physics will be important to manipulate and to braid these Majoranas. Okay, so now we have to add to the non-interacting part that we've discussed so far. We also have to add the charging energy of this island. So let's first of all think that these things are closed. So the charge on this is now well defined. Previously, we had the chemical potential fixed. Now the charge is fixed. And if this is a sufficiently small region, then it will cost some energy to add an electron or remove an electron or a Cooper pair from this region. So there's some charging energy. let's call it EC. Now the gate voltage will want to put a certain number of charges into this box. And this charge, like in a classical capacitor, is just the gate capacitance times the voltage, the gate voltage that I'm applying. That's the number of charges that I want to have also on the other side. And then, then I have to square this. I didn't draw this right. Okay, so like this. Okay, and EC is E squared over some capacitance that involves not only the gate capacitance but also other capacitances in the system. It's some sum of all sorts of capacitances. And now let's see what's happening with this thing. And perhaps it's good to first look at a conventional superconductor and to remember what's happening there. So let's plot the following. Let's put basically the gate voltage on one axis, and let's put the energy, the charging energy of the system on the other. And and now we will have different energies for different charges. So this gate voltage is something that I can tune continuously. So this is a continuous variable. But n times E, of course, can only take values 1, 2, 3, 4. We have an integer number of electrons on the system. So for each n, we get a different parabola. Okay, so it looks something like this. But now actually I have to add one more thing to the energy because it's a superconductor. If I add if I have an odd number of electrons, the ground state has not only the charging energy, but I also have to pay. I cannot put this one electron. The last one is unpaired, and since it's unpaired, I have to pay the gap energy. It has to be in the quasi-particle continuum. So it's plus either 0 if n is even, or delta if n is odd. So actually these parabolas correspond only to the even numbers so far. So I have n minus 2 electrons, I have n electrons, I have n plus 2 electrons. And the odd ones, for the odd ones, I have to pay an extra energy delta. So I need to shift them up. Do you have another color here? And let's assume, first of all, that so the charging energy, so this is basically these crossing points, they give you the charging energy, right? That's where the number of electrons and the gate charge just differ by 1. So this gives you EC. I wasn't good with units. This E should be here. If EC is an energy, at least it's better to write it like this. And maybe I should keep only one n. So I have n minus 2, n, and n plus 2. OK, so now let's shift them up, and let's assume that, first of all, that delta is larger than EC. So then this looks something like this. OK, where this is delta. OK, it's the extra energy. So now if you change the gate voltage, what you see is that you start out, say, with n minus 2 electrons. And at one point, the lowest energy state flips over to n electrons. So you add 2 electrons, and then you add another 2 electrons. So you add the electrons in pairs. And if you look at the current, if you apply a bias to this system, then whenever you're far away from these crossing points, there will be no current flowing. But once you're at the crossing point, there will be a current flowing because you can switch between n minus 2 electrons and n electrons, or n and n plus 2 electrons. You can add 2 electrons to the system and remove them again, and it doesn't cost you any energy. So at low bias, there will be a current flowing. So if you plot this, so whenever we're here, or here, there will be a current spike. Okay, this is the IDV as a function of V gate. Okay. Now we can drop delta and make delta a little smaller. Consider a slightly different, it's a different system that has a smaller delta. So let's say it goes, delta becomes smaller than the charging energy. Then it's going to look like this. Okay. And then what you see is that now actually these charge degeneracy points happen between n-2 and n-1 electrons, or n-1 and n electrons. So they differ only by 1 electron. And we have now what used to be just one charge degeneracy point split into 2. So now, in this situation, we're going to see something like this. So maybe the previous one was the green situation. And now we have a situation in which we have twice the number of peaks. Okay, and basically there are ranges where the dot has an odd number of electrons, which are small. So this is an odd number of electrons. This is n-1. And then there are regions which are larger, where you have an even number of electrons, which in this case was 2. So this n has to be even for this, right? So that I don't pay the charging energy. Okay, so you have some even odd effect in these Coulomb blockade peaks. Here, for the green situation, it's completely evenly spaced. But for the red situation, you have even odd effect, and you have twice as many peaks as you had before. So that's a totally conventional superconductor, and some good piece of good old mesoscopic physics. So now let's see what we would get with a topological superconductor. Right, so now we have these Majorana states sitting in the superconducting region on top. So there's these two Majoranas, gamma 1 and gamma 2. And they can, so there's a zero energy state that can absorb an electron. So what we used to pay an extra energy delta for accommodating the odd electron, but now this odd electron can simply go into this Majoranas, the fermion that you can make out of the Majoranas. So even and odd numbers of electron have exactly the same energy. And so this system now looks like this. We have they're not very different, but so the red ones are supposed to be the odd ones. So this is let's call this, let's say 2n. Then this is 2n plus 1. 2n plus 2, and so on and so forth. And they have now, they all have the same energy, at least the same minimum energy, because we don't have to pay anything to add in the odd electron. And so now the degeneracy points are here, right? And so what you expect in terms of it, if we now draw again the conductance, you expect that there's a peak here, and there's a peak here, and there's a peak here, and there's a peak here. And all of these, it's adding single electrons, not adding. In the green situation, we were adding pairs. It's also not like in the red situation, because we have this even odd alternation. Here, they're essentially the same distance from one another, and just charge E. Okay, so this is addition of single electrons. And that sort of immediately gives you one prediction for what should happen if you have such a quantum wire, and what one should be seeing if this is really realizing topological superconductivity. So imagine you do the following experiment. Imagine we increase B, and we look, and here we plot the gate voltage, and then I make a color scale plot with chalk of the IDV. Okay, and I'll just draw the peaks. So they were the peaks at 0b. We are not topological, so we will get some peaks which have some spacing. They maybe initially don't depend much on the magnetic field, right? And this corresponds to addition of 2 electrons every time I increase the gate voltage by enough. But now we have here somewhere the critical magnetic field where you go into the topological phase, and this Majorana states form. And now you know that in that region you should be having twice as many peaks. Right? You don't have only peaks every time you add a single electron, 2 electrons, but every time you add a single electron. So this should somehow start to look, well, maybe I exaggerated a little bit here, like this. Yeah, all these peaks should split into 2 around the critical magnetic field. Okay, and that's actually Charlie Marcus did this experiment just recently, and you should look at it. It's Albrecht et al. Nature 2016. So it appeared in Nature a couple of months ago. Okay, and it sees exactly this sort of picture. You find this plot, this measurement in the data. Actually, he could do even more. It turns out that there is still a small, even odd effect, because this is a finite size wire, and these Majoranas are still slightly overlapping, and they have a tiny energy. And this tiny energy, and so this leads to even states still having a little less energy, costing a little less energy than the odd ones. So that the even plateaus last longer than the odd ones. And then he can look at this spacing, the difference in the in the plateau lengths, and look how that scales with length. And so this is basically the Majorana. In the interpretation, this would be the Majorana, the energy of the hybridized Majorana, the Majorana hybridization, I should add, right? Right, and then he puts it on a log plot, and it has exponential. So it looks exponential, e to the minus L over xi, which is what you would expect, and with a reasonable value for the coherence length, or the Majorana localization length. So that all looks very nice compared to expectations. Pardon? Well, so the one thing, well, there's a very trivial interpretation that you can give. If it was a normal state and not superconducting, you would also expect the addition of single electrons. So you have to make sure that there is actually a gap opening again. So this region has to be gapped again, and they claim that it is gapped, and it's not consistent with normal interpretation. Okay, so but that's something that one definitely has to check carefully. Okay. So no, this is, but maybe the number of points here is finite, and it's different samples with different lengths that you're putting on the same plot. Maybe you would not be totally convinced by this by itself. So I don't know. I mean, if you want to be skeptical, then maybe you could just do. Yeah. Pardon? Right. Well, yesterday we did the calculate. So the calculation I did yesterday is something that is sort of is valid for these add atom chains. It very much used the fact that it's a very 1D system, and so it turns out that for semiconductors and superconductors, you probably have to be a bit careful with this calculation, because the semiconductor has a much larger Fermi wavelength than the superconductor. Right, and so it's not really so strictly 1D from the point of view of the superconductor, and that's something that I used yesterday very essentially. And then there's another effect that the Fermi wavelengths of the semiconductor and the superconductor are very different, and was also not the case yesterday. So I think that this calculation was very good for the add-atom chains, but it's not at all clear to which degree it applies to the semiconductor wires. Actually, I think it doesn't apply very much. Okay. So here you get this, I think it's 250 nanometers or so is what comes out, which is in the ballpark of what you would get from putting VF over some gap that is reasonable. Where is the wiper?
So what about teleportation?
Getting there. Next. So now that you can ask yourself how does the current flow when you're on these peaks, right? So we are in this situation. We are somewhere in the vicinity of one of these crossings. So you have a degeneracy between two states. They differ by the fermion parity. It's an odd and an even state. Okay, and so basically you're tunneling through a two-state system. Right, because it's just two charge states that are relevant, and you can write down a Hamiltonian for that. Simple. So we have a left lead, and we have a right lead, and we have our two-state system. So there's some energy delta, splitting delta, and this is basically, in some sense, it's the occupation of the Majorana. It's the thing that distinguishes between the even and the odd states. Okay, and then we can tunnel between the leads and the superconductor. So there's some coupling to the left lead. So we can tunnel into the left lead and go from, let's define it in such a way that D, how do I want to do it? D is from the odd state gives me the even state, and D acting on the even state is equal to 0. Okay, so D dagger D is an even state. D dagger D equals 0 is the even state, and D dagger D equal 1 is the odd state. So if I go from the odd state to the even state, I'm losing one electron, and I can put it into the lead, and I can do the same thing on the right. Like this, and then I can of course do the Hermitian conjugates, the other processes in which I go from the lead into the dot, and then I have the dagger in there. But this is really just resonant tunneling all over again. And through a single spin, I mean, there's no spin anyway, but non-degenerate level. Okay, and we had already this resonant tunneling formula, so now we know immediately what this looks like. Let's do it at 0 bias. Then we get E squared over H. There's no spin degeneracy, so it's E squared over H. It's like a normal tunneling through a single level. And so we have gamma left, gamma right divided by delta squared plus gamma left half plus gamma right half squared. Okay, so we basically have resonant tunneling, and so we get a conductance that is at best E squared over H, but now there is no symmetry because this is just the left lead, the left junction and the right junction. They need not be the same. So this is just at most E squared over H, but it doesn't have to be equal to E squared over H. As you go away from the charge degeneracy point, the conductance drops. But that's all not so important. The main point is that resonant tunneling is a coherent process. And despite the fact that these Majoranas are can be very far apart, you have a coherent process, and the coherence doesn't decay with the distance between the Majoranas. Okay, and that's what Liang Fu called teleportation. of course, you should remember that one of the conditions is that the bias that we are applying is less than the charging energy. We need to have this. We really have to be able to focus only on these two levels. So that we should be less than the at less than the charging energy. And if you make the system too big and you want to teleport from here to wherever, then the charging energy just becomes incredibly small, and the voltage has to become, and temperature and all of that would have to become incredibly small. So it's not that you can take this to extremes, but at least it's interesting that you can have this coherent process that is, in some sense, not not distance dependent. Lambda L only involves this, is actually just something that involves the coupling to the lead and the wave function of the Majorana at that end of the wire, and the wave function of the Majorana at that end of the wire for lambda R. Pardon?
Doesn't matter that D.
No, so the Majoranas are localized on one end, on the other, and the localization enters into this factors lambda. So the more localized, the bigger lambda, right? Because the more of it is sitting really at the end of the wire.
It doesn't matter that you.
They don't see each other at all. There's zero overlap between them, right? And yet you have a coherent process in which an electron comes in on one end and another, another, I don't know, there is no other, but an electron comes out at the other end, and it's a perfectly coherent process. You can make interference experiments with this, and it would be perfectly coherent. Okay, that's the remarkable thing. Small delta is if you have this two-level system of the two charge states, and if you're exactly at the degeneracy point, delta is equal to 0. And if you go away, then these two states have a different energy. And then that's delta. So delta is basically proportional to the difference of the gate voltage away from the charge degeneracy point. Okay? Good. So the point is that we're dealing with two different domain vaults. And one has this slope because we're going, maybe, I don't know which way it went. If this is trivial, this is, remember the mass changing sign, right? No, I probably want it from positive to negative. But it doesn't matter. Anyway, so we have two different slopes, and that then if you look at the Majorana wave functions, they look slightly different. There's an these extra factors of I in there. Okay, you're just. Yeah. So let's assume that. Let's assume that the lambdas are real. Otherwise, so the wave. Otherwise, the Majorana wave functions are real. It's up to. We can at least choose a gauge in which that is the case, and then there's only this factor I. And it's this fact that we have two different domain vaults on the two sides. Say it again. It's because the Majorana is in the fact that you have this degeneracy between even and odd electron numbers. And
superposition D and D diagonal?
Yeah, and then also it's the point is that so in some sense, if you were doing it perturbatively, you probably see it more easily. So there's some t left, t right, times the Green's function of in the superconductor, and because so the t to infinity is in some sense in order to make it small bias. And it turns out that this has some contribution, which is psi left, psi right, which are the Majorana wave functions in the left and the right. And it doesn't decay with distance. It has just this contribution, this Green's function. And then it's plus or minus depending on whether this is in the even or in the odd state. Okay. So you see actually that this if you fix this system to an even or an odd state, there's a there's a contribution to the Green's function that doesn't decay with distance. And that's the underlying thing that produces this. OK, let me move on. I want to get to. So now we need to add one more ingredient in order to manipulate Majoranas properly, and that is, and now we don't want to do transport any longer, but actually just manipulate, so I don't have any biases or anything like this. So we just have the superconductor, I have a gate voltage like this, and then what I want to do is I also want to add here some bulk non-topological superconductor. And let's assume that here we have again some gates by which I can turn on and off the coupling between this, this quantum wire and this bulk topological superconductor, bulk non-topological superconductor. Okay, so we have now not only the charging energy, but there's also two superconductors, and these two superconductors can have different phases or the phase difference between them, and there is some Josephson coupling between these superconductors. And so if you so basically, and you can tune this Josephson coupling simply by turning on and off this junction. So this one controls the Josephson coupling, and so if I have to write a Hamiltonian that not only includes the charging energy, let's call it QE. That's just this gate C. Well, we can still call it CV, CG times VG divided by E. But now I have to add the Josephson coupling, and let's assume that let's not think about it too much, and it's also actually pretty good. Let's assume that this Josephson coupling just has the usual form. There's a cosine phi energy for this Josephson junction. Now, one thing you probably know that there's a fractional Josephson effect with topological superconductors, and that has 4 pi periodicity. Here I only write 2 pi periodic term. And the reason is that this is not a Josephson junction between a topological superconductor and a topological superconductor. That's when I get this 4 pi, but it's between a topological superconductor and a conventional superconductor. And then I only have Cooper. Here I can only have Cooper pairs. So I can only transfer Cooper pairs, and then I have to have this cosine phi. I can only have cosine phi, not cosine 4 pi. Okay. So now we have to look at this problem, and then you know that the number of Cooper pairs and the phase are canonically conjugate, and the number of Cooper pairs is essentially this n. The fact when the deviation of n from even just determines whether my wave function, it turns out, whether my wave function is periodic or anti-periodic when I change phi by 2 pi. So basically I have a problem which looks a lot like a band structure problem. This is momentum. This is position. And the momentum is shifted by a constant. So if you remember, so band structure theory, if V of x is my periodic potential, and I already took the e to the ikx factor out of the Bloch wave function, then I get p minus k. And this is the Hamiltonian for the periodic part of the Bloch wave function that determines the bands. Okay. So this looks exactly the same. So the gate voltage basically acts like the Bloch momentum, and here we have a periodic potential. Okay. So now we can just use all our intuition from band structure theory to write down what the energy spectrum is for this Hamiltonian.
So in here you're not including quasi-particle signal.
But so they are in some. N can be even or odd. This is n is Cooper pairs. And so it turns out basically if you go 5 to 5 plus 2 pi 5 plus 2 pi.
That's phi is electron phase, or
This phi is the phase across it. That's just the phase difference of the superconductors here. Okay. But what you know is that all the fermion operators get a minus sign if you do that, right? So if you have an even number of electrons, then these minus signs in a many-body wave function, these minus signs just go out. But in the odd, you have a minus sign. Okay. So basically, you can sort of keep only the even part and account for this extra even or oddness by taking either a band structure problem with periodic boundary conditions or with anti-periodic boundary conditions.
so you don't need the cost delta of the excitation across the gap.
No, this I don't need anyway, because that's only for the non-topological superconductor, right? It's a topological superconductor here, and this thing has it can accommodate even or odd numbers at the same energy, because I have the Majoranas here. Okay. Okay, so now let's draw this spectrum for a few cases. So maybe the easiest one is if EJ is much less than EC. Okay. In that case, we already drew it over there, because now it's basically all charging. So again, I have this, and I have this, and then I have the odd one in between. Okay. So now I can still also think what this term does. Basically, this adds Cooper pairs to the superconductor, or removes them. Right, e to the I phi shifts the number of electrons by 2. And so this Hamiltonian still preserves fermion parity. So anywhere where I go between, say, an odd state and an even state, this is not lifted by the Josephson coupling, because I can only add 2 pairs of electrons. This is protected. But these crossings will open because of the Josephson coupling. Okay. And so on throughout the whole structure. Then I can look at EJ roughly equal.
So how come I don't expect this crossing is a normal band structure? What's the difference?
Pardon?
How come I don't expect this crossing is a normal band structure?
Here you would they would go away. Yeah, because you don't have this thing. I mean, basically, well, first of all, this is integer, and this one shifts you only by 2. And so there's sort of some additional symmetry, because you can couple only every other side, in some sense, right? And that makes this every other side in momentum space, but still, it's different from what you would usually have in a band structure problem. Okay, so this was the gate. So now basically we find, let me see whether I can, I have something like this and something like this. So this is the even one. This is with periodic boundary condition, and with anti-periodic boundary conditions, I basically just get the inverse of it. And then I continue with this. Did I draw it correctly? No, of course I screwed up. So it's the other way around, so that it fits to the picture on that side. So now this one develops from this anti-crossing. So it's going to be like this. And then there's another one like this. Okay, and so on and so forth. So that's some structure. And then I can go and open EJ completely. Right, and then basically the charging energy goes away. And what will happen is that the states now, they're basically, it's a cosine phi potential, so there will be states that are slightly, that are only very slightly coupled. So this periodic potential is very, very deep. And so you have sort of a tight binding limit. And so you get some bands that are very flat, very weakly dispersing. And I'm exaggerating here that one can still see something, but it's a very weakly dispersing bands in that limit. Okay, and that's basically where you have your Majorana degeneracy. You have a degeneracy between even and odd, which is due to the Majorana. Okay, so this is really this topological degeneracy in the system.
What boundary conditions are you talking about?
The boundary condition is what happens if I do phi to phi plus 2 pi. And then I have either periodic or anti-periodic boundary condition, because in some sense this n is even or odd. You can also think about it this way. So you add an extra 1 there, which you can get away. You can do away by just shifting with some e to the I pi times n. Is that right? E to the I pi times, which e to the I, I should shift n, so it's e to the I pi times phi, I think. I don't have to do it. No.
You say again where the capital delta is here.
Delta is basically, let's assume that delta is infinite, very large. So definitely I want to, what I'm doing now, I want to have delta much, much larger than EC, because I never want any, I mean, at least for the manipulation in the end, I want these crossing points to be far below the continuum, so that these electrons don't disappear into the continuum in some way. They should still be kept in the gap. Okay, that will be important. So here, I simply assume that delta is large, because that's what you have to do in order to manipulate properly and not have to deal with the continuum states. Okay, so the first thing that you can use this for is you can read out the states of this pair of qubits. So there you can basically now convert fermion parity, so the question whether you have an even or an odd number of electrons, to charge. Okay, so imagine that we're tuning our gate voltage somewhere here. So you're just not allowed to be exactly here. Then the blue one, so you increase the charging energy, or you decrease the Josephson energy from here to here, just by playing with this tunnel barrier between the bulk superconductor and the topological superconductor. And then this blue state corresponds very clearly to a particular odd number of electrons. And the white one is almost on the neighboring even state. So the two of them differ now by charge. And you can just measure this charge in the vicinity. And in this way, you can tell whether you were initially in the blue state or in the white state. Right? So you can convert the fermion parity to charge. Another thing that you can do is you can also do it with a dispersive measurement. For example, you can go here, and then what will happen is that, again, the blue one is very firm on one charge, but the white one comes out of a degeneracy between two charge states with, say, n and n plus 2. And if you move a little bit to the left, you get to this charge, and if you move a little bit to the right, you quickly get to that charge. So the white one, this charge will vary quite strongly as you change the gate voltage at that point. Okay, so the two things are very different in how the charge responds to the gate voltage is very different between the white one and the blue one, and that's something that's called quantum capacitance. So it's basically dn dv gate, and that is large for the white one and very small for the blue one. So let's call this delta C. So this basically acts like an additional contribution to the capacitance. So if you put this, say, into an LC circuit, you will see that the frequency shifts, the resonance shifts between depending on whether you're in one or the other state. And that's apparently something that experimentally can be measured very accurately and relatively fast. Okay, so this is a way of actually measuring which of the states you're in. And the charge measurement, the simplest thing is to put a quantum point contact in the vicinity, and then depending on some voltage that you're applying to pinch off this point contact or to make it open, you have these conductance steps. And if you tune the system to one of these steps, then a little charge in the vicinity will just slightly tweak this point contact and change the transmission. And since you're on this step, it's this conductance varies relatively rapidly with the charge, and you can just detect these differences. So that's how you would measure the difference in the charge. It's at least one possibility to do this. Okay, so now we know how to measure the parity state of our of these two Majoranas, or any two Majoranas. Yeah.
So first of all, am I understanding correctly that where you want to be in the large dose manipulation, and then we're going to move into
Absolutely. So whatever topological you want to do, you have to have this. You have to the states as degenerate as possible. You definitely want to be in this regime. And so one of the conditions is that we can tune the system such that EJ is much larger than EC. That's an absolute necessity to do any sort of topological manipulation. But if we want to measure, then we sort of turn off this Josephson coupling by closing this, and then the two states will be distinguishable in this way because they get different energies.
Then when we're changing the Josephson coupling down in that process, that has to be done adiabatically, right? And that's adiabatic. Which gap is in this situation?
Right. So in principle, it should be adiabatic compared to the whatever higher energy fermionic states you have. So let's say the gap of the topological superconductor. Okay. It's not this gap. Well, that actually, let me think for a second. So where does this, so what did I say? Yeah, no, probably you have to, yeah, no, so it's very good. So you have, it has to be slow compared to the gap and compared to the charging energy. And this is basically the charging energy kind of, well, yeah. So I think that's what you should also be careful against this gap. You have to do it slowly enough. But so if there's all of this is discussed in a paper. I should give the reference because actually the first author is here. And also if he wasn't here, I should give the reference for that matter. And I think I even wrote it down. 1511. 05153, I think. It's many authors, and they discuss all of this, and they also discuss these sorts of questions at length. What do you really have to do in order? What are the conditions that you need to satisfy in order to do this? Okay. So this is a collaboration of Jason Alicia's group and Charlie Marcus's group, basically. Good. Well, 10 minutes for braiding should be enough. 15 actually I still have, so should be good. Okay, so now how can we do braiding with it and maybe do some interesting, or Charlie Marcus, how can you do braiding with it and do interesting experiments? Basically we will do this sort of T-junction that we already discussed in the first lecture. And so what we might want to do is something like this. And then We have these bulk superconductors at all 3 ends. And I can close, and I have actually 2 wires here, two wires here and another vertical one. And let's assume that we start out the system in the following way. So instead of drawing these gates that turn the coupling on and off, let's just draw little switches. So this valve is open. This one we also open, so both at these ends we are strongly coupled to the bulk superconductors. These ones, let's close them initially, so there's no coupling. And let's also close the one down here. Okay. So what do we have? We definitely have two topological regions of 2 topological superconductors here and here. Right? They are strongly coupled, strongly Josephson coupled. So there's 2 Majoranas here and 2 Majoranas here. So we have 4 Majoranas altogether. Let's just go through gamma 1 to gamma 4. And then we have one island that is decoupled from the bulk superconductor. So this is charging dominated. So if it wasn't charging dominated, there would be 2 Majoranas. There would be one here. The color is really not visible. Distinguish. Let's do it in blue, maybe. So there are, in some sense, 2 Majoranas, but they are gapped out by the charging energy. So they're not at 0 energy now because of the charging energy. So this is, in some sense, not a topological superconductor. The 0 energy Majoranas are these 4. And let's say what we would like to do is to exchange gamma 2 and gamma 3. Okay? But on the other hand, gamma 1, gamma 2, gamma 3, gamma 4, actually, they make really a topological qubit because they have 2 evens. So you have 4 states altogether. 2 of them are even and 2 of them are odd in fermion parity. And we can, for example, take the 2 even states as the logical states of a qubit. Okay. So let's maybe, so we have F12, which is 1/2 gamma 1 minus I gamma 2. And we have F34, which is 1/2 gamma 3 minus I gamma 4. And the logical qubit states, let's say 0, which is 0, 1, 2, and 0, 3, 4. And 1 is 0, is 1, 1, 2, and 1, 3, 4, where this 0 and 1 just give me the occupation of these fermions. Okay, and both of these are even states because it's 0, 0 or 1, 1. Okay, so they both have the same fermion parity. And now we can ask what happens with this qubit if we're exchanging Majoranas to 2 and 3. Okay, so compared to what we discussed 2 days ago, we basically just have these 2 extra Majoranas out here, gamma 1 and gamma 4. They were not part of the story 2 days ago. Then we had only 4 Majoranas, 1, 2, 3, 4, with 2 of them initially coupled by delta 3, by the coupling. Okay, and here now we do this by the gate voltage. Yeah, so we basically have them. So I don't know if you, to help the memory, what we had was delta 3, and then we had here so let's do this with triddles. Looked like this, right? And initially we had delta 3 turned on, and these 2 were decoupled from the center. So these 2 Majoranas are these 2 guys, and these 2 Majoranas are the 2 that we want to braid. Okay, so it's exactly the same. And now we can not only couple these 2, but by opening these gates, we can also couple these 2, and we can couple these 2. And that would correspond to coupling these 2 guys and coupling these 2 guys. Okay, so now it's you can already see that you can just follow sort of the same logic by opening and closing the right valves and effectively get braiding.
So how do you visualize the difference
Well, just right. Yeah. Okay. So I said this. Well, basically now, what we can do is we can go somewhere here, put the gate voltage wherever we want, and wait long enough. Okay, and then we know we are going to be in the ground state. And then depending on you know that you're in an even or odd state, and then you just turn the Josephson coupling back on, and you know which state you're evolving into. Okay, so we can use this not only to read out, but we can also go the other way. We can just have the system relax to a particular charge state that we know, and then evolve into one of the two degenerate states of any pair of Majoranas. Okay, so that we basically can control what we start with. Okay, so I'm not going to draw all the outer things. These outer superconductors are there. So the first thing that you want to do, let me see which way around these ones remain open. Now this one remains closed. So we have got gamma 3 here, and let's first open this guy, and let's open this guy. The second one is not really essential, but let's do it anyway. So what we do with this is that now there's one long topological superconductor all the way down to here. Okay, so now these two guys hybridize and become finite energy, but there is another Majorana sitting here. So in some sense, what we've done is we've taken gamma 2 from here down to the bottom of this vertical part. So gamma 2 is now down here. Okay, and now the next steps. The next thing that we will do, in order not to draw the whole thing again, let me do it like this. So let's open this and close this. Okay, so now this gamma 2 goes all the way down here, so this one is gone. But here now, this is where gamma 3 is moving. And then finally, I'm just closing this off again, and I'm closing this off again, and this moves gamma 2 to here. Okay, so if you didn't manage to copy this, which I suspect, it's in the notes and that are online, and it's also in this paper, so you'll find it there. Okay, and as a result, we started out with gamma 2, gamma 3, and now we have gamma 3, gamma 2. And we've done exactly what we calculated on Monday. And so the braiding matrix, the braiding will produce exactly the same transformation, U34, which is exponent of pi over 4 gamma 3, gamma 4. And you can convince yourself with a little bit of algebra, one line, that what this does to this logical basis of our qubit is that it's exponent of pi over 4 sigma x and then I probably. Let me make sure that yeah. Okay, so basically what this operation does, it flips the state of the qubit from 0 to 1 or from 1 to 0. Okay, and so now we can try to see whether yeah, it's good. Huh? Did I write 3, 4? Yeah, it's 2, 3. Thanks. Yeah, sure. Okay, so now let's do the following. Let's start with the following situation. Where all of these valves are closed. So, and let's initialize. So we said that we can initialize these in any way we like by the procedure that I just explained. So let's assume that we initialize the system in 0, in the logical 0, which is 0, 1, 2, 0, 3, 4. Okay, and now we have it initialized. Then we open these valves, and then we are in the initial state of this. So now we have our qubit, and we know in which state this qubit is. And now we perform such a braid operation. Okay, just as I explained, and what you find is that you should go to the 1 state, right? Because it's what you do is sigma x. But if you think about it, if previously we had 0, 0, now we have 1, 1. So basically 1, if we now in the end sort of go back and close all the valves again after we did the operation, we're back in this situation. And now we are closing all these valves again. So we know that we should now be in this 1 state. And let me see, am I doing this correct? I think it's correct, yeah. No, but something is funny. Where did I? Yeah. So something was funny, and I'm sorry. It's actually sigma x flips, but this is still an exponent of sigma x. So exponent of sigma x is 1 over root 2, 1 plus I sigma x, right? That's what I overlooked. So if you do this operation, you have half the times, or with amplitude 1 over square root of 2, you stay in the same state. And with amplitude 1 over square root of 2, you go into the flipped state 1. So now we're actually not in 1, but we are in 0, 0, plus 1, 1 up to phases. We are half the time we're in 0, 0, and half the time we're in 1, 1. And if you now make a measurement of the charge, in this state, you should find the original charges, say Q left, and Q right. And here, the one charge has to move. Each one changes the parity. So this has to change by 1, and this has to change by 1. So here, we have again Q left, Q right. But we are in an superposition, say, with Q left minus 1 and Q right plus 1. And so if you now measure the charge, half the time you should measure this, and half the time you should measure these charges after braiding. Okay? So that's a clear prediction. Now, you can always charge can jump by some accident, but what you can do also, you can do 2 braiding operations and then do the whole thing. And I mentioned it briefly at the end of the first lecture, 2 braidings. So U23 squared is basically gamma 2, gamma 3. And I'm not careful now about i's. But gamma 2, gamma 3 was just sigma x. Okay? So if you do 2 braids one after the other, then indeed you get sigma x. So then instead of getting from 0 to a superposition of the 2 parities, you go to the 1, 1 state. Okay? And it's always the 1, 1, so you should always measure these charges. Okay? So that's something that is quite would be quite remarkable to see. If you make no braid, you simply stay there. If you make a single braid, you go into this linear combination. And if you do 2 braids, you go into the other basis state and you change the charges.
I think the superposition can be a classical, like a mixed state, 50-50 between the two.
Right.
What's the status on the coherences?
Well, so I think that's why you want to make the braid squared experiment, because if it was a mixed state, this braiding squared will not undo this this mixing.
That'll check.
And that basically, in some sense, checks the coherence, that you're really doing what you're. That's why you want to do this on top. Okay. More questions? Yeah. Yeah. Yes. Well, it's in exactly the same sense in which we do exactly this. So it's exactly the same way in which we move them from here to here, and then we calculated what happens with the ground state, how the state moves in the ground state manifold, and it gave you this unitary transformation. So, but I think there's 2 zero-energy Majoranas, and initially they're here, and then you move it up here. And they're here and here, so you really, in some sense, move it up there. I'm not sure that I want to talk about same or not same, but that depends on what. But the 2 zero-energy Majoranas are really trading places in the way that I described. So that's basically what I wanted to cover, and I think I'm out of time. So the situation right now seems to be that there's rather remarkable evidence that these things actually exist. Charlie Marcus says that, well, they exist. Now we need to do something with them. Maybe I don't know whether that's the optimistic way of looking at it. And so this looks quite realistic, and it will be exciting to see how this develops. There are also other experiments that are discussed in this paper that are slightly less demanding than this, but would be equally interesting, like probing the fusion rules of these Majoranas. And I should also emphasize that here I focused on this particular way of doing things, but there are other proposals, for example, by the Delft group that have a lot of similarities. Delft and Leiden group that have a lot of similarities with this and would in principle achieve the same things. So there's more than one path to success. So let's see how that works out. Thanks. Yeah.
Out of curiosity, is there any proposal for actually
Interactions on?
2 qubits rather than having a 1 qubit operation?
So in some sense, yeah. So you how to do C-naughts?
Yeah.
So I'm not sure whether it exists in this particular realization, but the Delft and Leiden people, they have thought about how in principle to do this. And basically you have to have parity measurements of sufficiently many Majoranas together with single qubit operations that would realize such a C-naught. Yeah.
That's in the case where you move one Majorana and then you take one of your electrodes and you scramble the balls, you turn off the superconductor and turn it back on.
Yeah.
Do you lose some of this braiding information?
Sure. So the gap has to remain intact and this and well developed at all times, right? If you
I'm saying you only turn off the superconductor a second. The 2 you're exchanging are still in a perfectly well defined topological.
yeah. And now which one do you want to turn off?
So let's say you move gamma 2 down, that's there, it's protected.
Yeah.
Then the one where it used to be, you turn that off. You turn off the superconductor.
Well, but there's still another one here that you want to keep, that you would also kill in that way.
Okay, so kill it and turn it back on.
Yeah, that I don't think is a good idea. I think I'd be surprised if this would not be detrimental. Well, well, first of all, turning one Majorana off is impossible. You always turn them off in pairs.
Right.
So then only these two are not involved in the process. I don't know how to turn them off so I have a hard time seeing that it and certainly it would kill the qubit information, right? The information that you store in the qubit.
It goes back to the question of the distinct
Yeah.
keep everything
Right.
easier
Right. Yeah, I'm also not sure that I like this idea. It's not involved. It's one ground state manifold that arises from all of these gammas, and in some sense there's an awful lot of entanglement between all of this, and there's nothing local here. That's the whole. Yeah.
then any kind of transience that you have when you're shutting off turning all your gates on.
Yeah, you have to be a good experimentalist.
Okay, so before we thank Felix again, I just want to remind you that there's an optional lecture today at 4. More depth than that. You should stick around for an optional lecture at 4. And let's thank Felix again.
Good. Pardon?
Can I ask you a question?
Sure.
So, when you're considering the Josephson junction between, say, S wave and some P